Hello to all. My name is Anna, and I will speak a little bit about the research we've been working on in transportation scenario planning with graph neural networks. We have every day millions of people commuting from home to work, and changes in the city, like the constructions, new traffic directions, it causes impacts that need to be measured so that the mobility of the area is not compromised. So the main question we aim to answer is how to plan human mobility considering the impacts of those changes in the city flows. We know that urban specialists more often than not rely on precedent data analyzed in isolation to make decisions, but with the growing availability of urban data and advances in machine learning, there are new opportunities to better support the exploration of possible alternate urban scenarios. So as motivation, let's take this mall. It was built in a previously empty area, and its construction is accompanied by several impacts on mobility. It can bring new bus lines to new region, for example. These impacts, they can lead us to ask some questions, such as, after the construction of the mall, from what regions will people commute to reach it? Or even how this new construction will impact the flows in the neighborhood. As related works, when we talk about scenario planning, there are many approaches that allow planners to analyze future outcomes based on present day decisions, such as regression analysis, travel forecasting models, econometric models, and more recently, machine learning approaches. When we talk about commuting flow prediction, we can quote the gravity model that in their modern extensions, it takes into account several factors such as demographics and land use, but it still falls short of properly modeling complex linearities. We also have the radiation model that uses only population distribution, but no urban data. And also more recently, we have machine learning approaches that are good at modeling complex linearities, but ignore spatial correlations, using only the characteristics of origin and destination. In an attempt to unite the strengths of each commuting flow prediction model, the GML was proposed, and it was previously tested in comparison to other baseline models and achieving better predictive performance. The GML it's for a geocontextual multitask embedding learner. It's a graph neural network model for commuting trip distribution modeling. And the model proposed, it consists of two components, the GML itself and a flow predictor. It makes uses of two data sets. The first one is a geo-adjacency network, unidirected weighted graph, where the nodes are the census tracts, and each node has its urban indicators, and the edges, they are weighted, so we can measure the strength of the correlations between two nodes. And in our case, that strength is defined by a trip duration. The model utilizes a graph attention network to encode the spatial dependencies into an embedding space and to disentangle the origin and destination characteristics that are hidden in the infrastructure and land use data. The GML employs two separate GATs to encode the geographic contextual information into two different embedding spaces. So we had a GAT of origin and a GAT of destination. Finally, we have the flow predictor that employs a gradient boosting machine as a regression model to predict commuting flows, evaluating the largest information gain of features. In the original GML model, it was proposed using extensive land use data from New York City. But in this work, we're interested in test the effectiveness of our methods in cities where there are still no resources to collect and process high resolutional data. So we focus our efforts on two Brazilian cities. The first one is Recife, the capital of the state of Pernambuco, northeast coast of Brazil. And the second one is Curitiba, the capital of the state of Paraná, south region of Brazil. Talking about the Recife source of data, we use the community flow dataset obtained from a survey carried out by the city administration, resulting in almost 16,000 pairs of commuting trips. And the urban indicators came all from Recife's open data portal. When we cross the two data sources, we end up with 52.3% of total census tracts information. Talking now about Curitiba, we also use a community flow data set obtained from a survey carried out by the city administration, resulting in almost 33,000 pairs of commuting trips. And the urban indicators were made available by Curitiba's Urban Planning and Research Institute. We crossed the two data sources and end up with information about 91.8% of total. In both cases, to measure the travel distance between the centroids of the census tract, the open source routing machine was used. We evaluate the performance of the model in both Recife and Curitiba, and these are the results for the test set. The model's performance for both cities are quite similar, with the RMSE being the metric with the most significant difference, although still small. This can be attributed to the difference in the number of commuting flows and census tracts used in Curitiba and Recife. Given that this number was greater in Curitiba, a lower RMSE was expected. To the scenario planning, we have the city data, but now we are using changing urban indicators. We use that data as input of our model, and the predicted flows, they are considering modifications in the city. In our first case study, we are interested in understand the impact of new bike lanes in the city. So we distribute 24 kilometers of cycle paths between 4 avenues that connect important points in the city. There are 4 avenues with high rate of daily vehicle flow. However, any type of cycling infrastructure, as you can see in the figures below. In the first figure, we can see the census tracts where we add the bike lanes in dark blue and tracks with centroids within 2 kilometers of distance in light blue. In the second figure, we show the community flow differences considering the new scenarios where head means flows that increase and greens mean flows that decrease. In the third figure, we have the histogram with community flow differences, and we know our results shows that the flows in the analyzed areas shows an average increase of 13%. In our second case study, now we are interested in the impact of new high-rise buildings in Recife, in the construction of 13 towers with size ranging from 13 to 44 floors in the former historical site of the José Estelita Pier. In this use case, we analyzed the relative changes considering all the census tracts, which shows an average increase of 12.5%. But the most significant changes, they happen in units close to the new project or in high density units that already have large community flow volumes, whose are predicted to increase by at least 25%. As conclusion, it is an initial work yet, but it is a tool. GML is a tool to assist planning and transportation researches in the decision-making processes, even considering cities in developing countries, but of course, it requires effective involvement of public administration. And as future work, we'll investigate how the model can predict changes considering multimodal commuting flows, and we will also validate predicted changes through data sets that have available time evolution. And that will be it. Thank you.
Oh, great. Thanks, Anna, for this great topic. And is there any question from audience? Okay, cool. Maybe just warm-up questions. So one small question that I thought that you gave some case studies about the cities, right? The Brazil and another one. It looks like it's only about the spatial information or spatial inflow things. Do you consider about the temporal change, like from the rush hour, things like that?
Not yet, but it's a future work also.